Welcome back to another TapRooT Podcast. This week I've got Justin Clark. And Justin, what is Equifactor?
Oh man, I'm glad you asked, Alex, and it's good to be here. So Equifactor is an equipment troubleshooting framework to help us gather all of the what around equipment failures. So you can never understand why something broke unless you understand how it broke. And so as we're gathering evidence for a TapRooT investigation, we want to make sure we understand everything around how the equipment failed. And this can be used for everything from your clothes dryer at home, we've used it many times, and all the way up to multi-megawatt turbines. So we have pumps, we have compressors, we have transformers, all the way down to electrodes and diodes, all kinds of different equipment in standard troubleshooting tables.
So it's a troubleshooting process.
Mm-hmm.
And it's got a list of different tables that help people that may or may not have expertise gather information.
Absolutely. Yep, and so these tables are all structured to tell you everything you need to look at when you see certain symptoms. So let's say I have a pump that fails and its mechanical seal was leaking. When you just have experts in a room that get together to do the troubleshooting, they're always going to come up with the same questions or things they need to look at, things that they're going to check first, second, third, and so on. What we want to do is give them, give our troubleshooters, whatever their expertise level, all of those same questions or things that you need to look for so that they can just check off a list. Because what we really want to do is get operations back up and running as fast as possible and make sure that the problem doesn't happen again in the same way.
So I think back to my days in operations and as a manager, we would have a piece of equipment that had dealing with a quality issue of some sort. Mm-hmm. Most of the time, it's not like the equipment just didn't turn on. It was something wasn't right. We're noticing an issue, so we call in maintenance. Now, my maintenance guy Doug would come in, and he was the lead guy. He knew everything about the piece of equipment. And he would come in and he'd have a list in his head. Mm-hmm. Well, it could be the drivers, could be the ball screw, could be this bearing on the spindle. And he had all these things that were possible, and he'd break them down as best he knew. Mm-hmm. Now, we all have a Doug, right? Everybody's got a Doug somewhere in their facility that's the equipment expert. But what do you do when Doug goes, I'm not sure?
Uh-huh. Yeah, so there's a few different things. These people are the experts for a reason. They have all of the experience, all of the knowledge. They are the ones that know the most about the system probably in the world. But eventually, they're going to run into new problems and maybe new pieces of equipment they haven't dealt with. And we need to have something that allows us to get beyond what we already know, right? And so in Equifactor, that looks like either we build another custom table for that, or we can start using another tool like failure modes or failure agents. All physical equipment is going to follow the same laws of physics, and so there's only really so many ways that they can break. In our failure mode section, we have basically every different type of failure mode you can see, whether that be brittle fracture or galling and spalling, or all these different types of terms you're going to hear from a laboratory, a materials laboratory, so that you can start focusing in on here is exactly how the equipment failed, and then the next step is going to failure agents, where you're looking at all of the drivers for that particular failure mode. So let's say we had brittle fracture in a pump shaft. There's a whole bunch of different prerequisites for brittle fracture, and these are all going to be what we look for in the FRET framework. So this is one that Heinz Block started and propagated. It's a way of thinking about looking for what causes failures.
So you mentioned Heinz Block, and I think for our group we should take a step back and really say, what are these? Mm-hmm. So Equifactor is a list of tables and a process for helping people break down and troubleshoot. Mm-hmm. Where did it come from? Where do these tables come from?
Yep, so Heinz Block. Back in the 1990s, Mark Paradise, the human performance expert, partnered with Heinz Block because he was the equipment troubleshooting expert with ExxonMobil. He traveled all around the world to refineries and rigs and did the troubleshooting for all of the complex failures that they couldn't figure out themselves locally. And he started to see a lot of patterns for what is the most likely thing that causes these failures. And he compiled all of that experience and knowledge into actually that book right there, Machinery Failure Analysis and Troubleshooting, that has, here are all of the symptoms that he ever saw for process equipment and all of the possible causes that he either saw or people suggested that could be possible causes. And so what he compiled was a list of all of the troubleshooting tables, and we partnered, TapRooT partnered with him and to use his tables in the troubleshooting process back in the 1990s. And since we've expanded those outside of the oil and gas industry, and now we have a whole bunch of different other tables as well. So it's taking all of the expert knowledge and experience and putting it basically in a troubleshooting checklist. But that's where the Equifactor tables came from.
Now, you mentioned there's different tables. So what are the different, we'll say, categories of tables that people use when they're using Equifactor?
Yep, so there are many, many different standard tables, everything from pumps to valves, gearboxes, gas turbines, compressors, everything to fire pumps, and you can even, and then the next step would be designing your own tables.
So we've got a list of standard tables.
Yeah.
That's equipment, that's valves, that's electrical. So that those have a long list of different things, AC motors, DC motors, like we said. We're naming them off. There's a bunch of those standard tables that Heinz built, we've added to. If I don't have one of those, if my equipment is maybe more unique or it's very specific, what do I do?
Or from an industry that
doesn't have pumps,
oil and gas,
or oil and gas specific. What would I do if I didn't have a table?
Yep. So this is where you want to design a custom table for your team. Let's say I have a fleet of Wamodine compressors that are not in the tables. They're a very specialized piece of equipment that operates a little bit differently, let's say. You want to sit down with your design engineers, you want to sit down with your operators and maintainers so that everything that they have seen they can put together. Because when it comes down to, eventually equipment's going to fail, and we want to make sure that we have everything pre-gamed to give our people what they need to get that equipment back up and running as quickly as possible. And this is where you pull in failure modes and effects analysis. This is where you pull in all of your failure records. So when we see, those compressors fail once or twice, if we've never seen that before, we want to add those to the Equifactor table so that next time we see that symptom, we know here are the possible causes we need to be looking for. And this helps us to learn as an organization from when our equipment fails and prompt us to go back and update some of our design documents, our failure modes and effects analysis with this new failure mode that we didn't think because it's integrated with another system or there's an environment that we didn't consider, things like that.
Now that sounds really hard to do, Justin. Is it difficult to build a custom table?
Actually, it's one of the simpler things to build in the TapRooT system. And we do have some new tools that just came out for importing from an Excel spreadsheet so that you can put hundreds of tables, let's say from your failure modes and effects analysis, right into the TapRooT software. And then with the click of a button with that import, everybody globally that cares about that equipment can go in and look and see all the new tables.
Now, how do I, if I'm at my piece of equipment, how do I get access to these tables?
Okay, so there's a couple different ways. First, all the tables in the TapRooT system are in the Equifactor book, so if you are in a plant that you can't have anything electronic, the book's your best bet. Next, you can pull up any desktop computer or any computer that has internet, and you can get onto the Equifactor module in the software. The final place you want to go is there's a mobile app. The TapRooT mobile app has all the Equifactor tables built in. And so when you go look at that, your operators out in the field can say, okay, I have this pump failure. Let's go look at all of my standard tables for pumps. And they're going to look at, okay, first I probably need to check the valve lineup. That's the most obvious thing that they're going to check. Okay, now let's do a clean and inspection on the suction strainer. Am I looking for damage on the lines? Is the pump spinning in the right direction? All of these things that get more and more obscure as you move down the list because they're ordered in the obvious and easy low-hanging fruit first.
Yeah, I think of it as more and more invasive. because it's like we
That's
used
exactly
to do when we'd have maintenance. I always think back to the same machine. It was the Mach. The thing was installed in the 80s. It was 2 stories tall, giant piece of equipment. And if you were going to do something, he's like, well, my guy Doug, he'd be like, well, I can check this, and it's a simple test, and it'll take about 20 minutes. If that doesn't work, then we're going to have to tear it apart, and that's going to take 12 hours. It's like, yep, do the 12-minute check. Let's do the quick check first, just to make sure that we don't have an easy fix, and then we're going to have to do the hard way and swap out a spindle and go troubleshoot in the other room. And so those are the kind of things that you've got to make those decisions while you're doing your troubleshooting and maintenance. Now, you mentioned with custom tables, you mentioned that sometimes there's maybe you just want to do failure modes and effects. What are failure modes and effects? What is this? You mentioned it a little bit. Let's kind of talk about that in more detail.
Yep. So a failure modes and effects analysis is kind of a proactive design tool that design engineers use, or system process safety engineers use, to kind of brainstorm beforehand every possible way that this process or piece of equipment can fail. And then all of the possible causes for each of those failure modes they build into the system and think about. And for each of those possible causes, they design in safeguards. And so we have all of these safeguards that should be protecting the equipment from failure, or the process from failure. And so that is a pretty large engineering design effort that you're going to have your team available, and that's one tool that people use to troubleshoot, is when they go in and look at, okay, we have all these possible causes for this particular symptom. Which one of these failed? Or is there someone that we didn't have because we didn't know about that possible failure? So that's one thing, proactive. An Equifactor troubleshooting table is kind of the opposite end of that, where here's our reactive, here's everything that we want to look for after the equipment breaks, in a structured, easy-to-use format that's not a really thick document, but really ideally a one-page checklist that we can go through and check that lowest hanging fruit. And what you want to do with Equifactor is take those failure modes and effects analyses, build Equifactor tables from them, because it's basically a one-for-one there. And then on both the proactive and reactive side, whenever you find anything new, then that's your prompt to go update both of them.
So your table's built, it's a series of equipment. You've got your equipment kind of breaks down into sub-equipment in a lot of cases, but we've got that equipment. Then you've got this list of symptoms, and those symptoms break down to
possible causes.
So those possible causes, I always like to refer to them as a physical cause, because it's not a root cause. It's not a causal factor necessarily. Sometimes they are, but it's the physical cause of failure of equipment. So you might have a symptom, low capacity. You can have a lot of possible things causing that pump to not be producing the flow that it should. And so we have a list of those possible physical causes: the filter, the fan propeller, all these different things that could be causing that flow issue. So we can create those. We can customize those tables. What's another thing I can use to help me troubleshoot equipment when I'm not able to use those tables? If I don't have custom tables and I don't have standard tables, what other modes?
Yep, and that's exactly where you're going to go to failure modes and effects analyses, where you're proving exactly how the equipment failed. And really what we're trying to do with all of these tools is, if your leaf blower at home just explodes or something, you're just going to tear that thing apart and start troubleshooting and figure out, okay,
or throw it away and buy a new one.
Yeah, more likely. We can't really do that with a giant steam turbine. If that failed, we don't want to break into it unless we know exactly what we're looking for, because especially with a big piece of rotating equipment, if we leave, and actually leave a wrench in the engine, that happens all the time. And if we don't have everything planned out, one, we're probably not going to find everything that we need to be looking for. Two, we might have to open it up multiple times if we're only looking for one thing at a time. And three, we may miss something that was an additional problem. A lot of times we'll see 2 or 3 different possible causes that were actually factors here. So maybe we didn't have a trip throttle valve set to the right point, and we forgot to drain some steam from a steam trap, and we were operating a little bit below or above our normal operating range. All of these things could be why a turbine blade got damaged. And so if we don't have a plan to look for all of those when we break into the equipment, then we're going to miss those opportunities for improvement. Once we find, hey, I found this smoking gun right here, we just didn't empty our steam traps. Well, if there were multiple other things going on, we're going to miss those. And then we could possibly even have the same accident happen again because there were other physical causes of failure. But like you mentioned, there's always the equipment failure itself is probably going to be a causal factor. That's usually the first thing in any major incident is the piece of equipment breaks, and then all the humans coming in afterwards and not responding properly or misreading indications or something like that usually ends up allowing the equipment failure to progress to a more severe incident. Now, once you find that causal factor, the equipment failed and here's how it failed, you really want to have a failure mode attached to it. It wasn't just the pump exploded, it was the mechanical seal was leaking explosive process fluid because there was grit in the process fluid that destroyed our mechanical seal. So you really want to have a failure mode so you understand what happened. So then I can start looking at root causes. Because there's all kinds of different reasons why a mechanical seal might start leaking, all of those physical causes of failure. But once we find out that, okay, there was grit in the system that put grooving in my carbon faces, well, that is the start of your root cause analysis.
Where did that grit come from?
Yep. Why do we have grit in this system? We might, that might expand the scope of your investigation.
What caused the grit? How did it get there?
Mm-hmm. Yep. Why didn't we not recognize that this grit was in the system? What other equipment failures has it caused? Because if there's grit in one portion of the system, it is everywhere in your fluid system. So all of these things we need to be looking at led up to the failure.
Now, you mentioned as well, you were talking a little bit earlier about fractures and reactive environment, the physics behind equipment failure. Mm-hmm. What in Equifactor talks kind of up to that physics side?
Yep, that is your failure agents portion of your failure modes and failure agents. And I mentioned the acronym earlier, but the acronym is FRET. There's only 4 failure agents in the universe for any physical equipment failure that drive failures. So FRET, force or electromotive force for your electrical types, a reactive environment that could be chemically reactive, biologically reactive, or nuclearly reactive. You have temperature, so high or low temperature. You can have oscillating temperatures, so a dynamic change in temperature. And then there's time in life. Beginning of life problems, the very, very, very particular beginning of life problems, or end of life problems. You should expect to see different types of issues, beginning of life and end of life. We're all familiar with the bathtub diagram of when equipment usually has problems. And so when you find a failure mode in equipment, you want to look for all 4 of those that could possibly be driving it. We mentioned brittle fracture earlier. Brittle fracture requires a whole bunch of different things, a susceptible material, a pre-existing flaw in the material, a tensile stress. And so if you see brittle fracture, you need to start digging into how did we get each of these failure agents in our system. Maybe if we had, we had a crazy vibration that caused a bearing to fail. Where did this vibration come from? Was it transmitted through the foundations? Was it transmitted through the piping itself? Is our equipment not balanced? What about the motor? There could be all kinds of different things that lead up to a bearing binding. And when we start moving into failure agents, it really narrows down the scope of exactly what we need to look for. And it's a game of deduction rather than educated guessing.
So I think back to, I had a client where they had a crane that was lifting a piece of equipment. And they attach these lifting, basically bolts that bolt in and lock in, and they lift this with a crane and the straps. and the bolt didn't fail, but the actual lifting fixture failed on it. And we were talking with this person, the shackle, and they were like, I don't know how this failed. It was beyond their expertise. They're a safety guy. They don't understand failure. So we're looking and talking through the Equifactor tables, and we're looking and say, hey, we don't have there's shackle bolts is not in the tables, but we're in failure modes and failure agents, and we're looking at fracture. I said, well, this is a fracture. You can look at it. Do you have a picture, or do you have the bolt? He goes, yeah, we have the bolt. I say, well, now there's two options. Option one is probably the best, which is you need to send that bolt out to somebody to take a look at and tell you why it failed. Now, I remember back in my material science engineering days, we had a metallurgy professor, and what they would do is they would do this a lot. They would give us failed things and have us look at it and analyze for failure to see what caused that failure, what type of fracture. Was it a brittle fracture, being something that's like a fast crack, versus ductile fracture, something that elongated, basically got past the plastic zone of a material before it broke. And then you have fatigue, and you can look for fatigue by looking at these little wavy lines that look like waves on a beach.
Yep,
kind of
little
thing.
Beach marks.
And that just so that crack would slowly propagate over time. And what that tells him, and he's like, well, why is that important? I said, well, what that tells you is this a thing that this is happening because we've done these lifting shackles so many times that they failed? That would be fatigue. Well, that would tell us, hey, we need to rotate these out at a certain point. They can't just use them to failure. We need to rotate them out every 200 lifts, every whatever. If it was ductile, meaning something like, well, typically the ductile, you're going over a tensile force over a period of time, meaning that it's elongating because you're just keep yanking and pulling until it pops.
It turns into taffy.
Exactly. Versus a brittle might be something else. So knowing what that failure mode was and what that fracture mode was helps people better understand what you're going to do to fix and control that. And so having that be as an exercise that people go through and understand those, how that thing failed affects how we might handle it from a replacement, a safeguard, something in place like that. So I think it's good to think about this from a physics standpoint. And maybe that's my material science background. I get it.
No, you're exactly right, because that tells you, it starts to tell you exactly the direction you need to go to prevent it from happening again in the same way. Because the most important thing we need to do is make sure that it doesn't happen again. If we don't understand what happened with any of those equipment troubleshooting tools, we're going to come up with all kinds of corrective actions that probably don't fix the problem we actually had. And that's the real important thing of proving exactly how the equipment failed. We don't want to guess. We don't want to make educated guesses. We want to prove it. And that's why it's so dangerous to, let's say, a lot of oil refineries do this. If they have a pump failure, the cost of a pump is pennies compared to their operational budget, but pump fails, and if it's a critical pump, your operations goes down with that pump. And if I don't figure out exactly how that pump failed, I can't prevent it from happening again in the future. This is one of the examples we use in the course, is they were just replacing pumps every time the mechanical seal failed, and that was a run-to-fail maintenance strategy. As it turns out, they had 23 unplanned outages because of those pump failures in a year. That's a ridiculous amount of downtime. That is just hemorrhaging revenue. And so just because they didn't take the time to understand that first pump failure, what is allowing this pump to fail, they automatically bought themselves into every subsequent failure that, really should have crippled their business.
So I think back to a story I was told by a global reliability director that I worked for. And they had a piece of equipment. It was basically a large aluminum rolling unit. And basically, aluminum would come in, get rolled down into fine sheet stock for can stock, things like that. And he was telling me they had this one piece of equipment, and it just kept breaking down. And it would take them 14 to 16 hours to go through, fix, repair, and get it operational again. Well, it had happened so many times that they had cut that downtime from 16 hours down to, I think it was 6 or 8. I can't remember exactly. And they were congratulating themselves on how fast they were getting at fixing this and repairing this equipment. And he said, like, you know, the management had to come and say, you know, yes, you guys did have great improvement on being efficient at repair, but we missed the point entirely, the fact that this keeps breaking down. We don't need it to break down. We need it to be operational and not fail. So it's great that you've got it down. You've cut the time in half or whatever it might have been. But we've got to understand what keeps causing that repeat failure. And I think that's exactly what you're thinking. Is like sometimes we get so obsessed with firefighting the problem and getting it operational again that maintenance and operations sometimes forgets to think, hey, what was the root cause here? What in our system is allowing this failure to keep coming up, and what can we do to put in place to prevent these things so we don't lose that? We had a piece of equipment, and we used to mark it as how much time was an hour. We knew that. How much time was down for a day, and how many dollars would you lose when it was down? And maintenance had that where each machine, they knew how much dollar amount was lost by lost time. So on the graph you could say, okay, we had 14 hours or 20 hours of downtime yesterday. Well, that's $200,000 or $1 million. Now, refinery goes down. If your crude, something important goes down, that's millions of dollars an hour.
Yep.
So high reliability can really make the difference in success or failure at your facility, but also in your industry. Yes. I think of you were on nuclear submarine. What is the cost of maintenance failures when it comes to a reactor?
Yep, that is a huge topic right now in the nuclear submarine force. Is you better believe the Navy has all of its operating costs and everything for every type of submarine and every crew down to the hour, and that's one piece of the equation. But then there's the actual mission that they're out there to do. These things, national sovereignty, you're not going to quantify that in terms of dollars. And so it's not just, okay, here's how much it costs the American taxpayer in, whether or not we have a reactor problem. But there's quite a few other things going on there. One is, can we be out there doing the mission that we need to do to make sure that America has the big stick that it needs to? But in terms just locally of the submarine, if you are underwater and equipment fails, where that's a life or death scenario, and you better be able to get that back up and running fast, or else everybody's toast. And so it is really critical to have all of that troubleshooting basically pre-planned out, so that one, everybody doesn't die, and two, we get the equipment back up and running in a way that prevents it from happening again. We need to learn from every failure, because even if you're just looking at dollars, reliable equipment that doesn't fail, equipment that we have prevented every failure that could reasonably happen, that's going to be the most profitable business. Because if you let operations go down, that's where you really start losing money. Nobody really cares about the cost of a pump. But once operations goes down and we're not bringing in revenue anymore, that's where our business is threatened. That's where survival is threatened. And so anything that allows the possibility of an equipment failure is a direct threat to our revenue.
Yeah, I could think of pumps themselves. You go, oh, well, that's a really cheap pump, but if we don't really care if it fails, we'll just replace it. But what's the time cost? Like you're saying, what's the time cost of that replacement? Maybe it's worth spending a little bit more money on this pump so that we save money on reliability and it lasts longer and we don't have to replace it as frequently.
Absolutely, and that is where we need to start looking at every equipment failure represents an opportunity to improve and an opportunity to upgrade. If you look at the cost of the total lifetime cost of a pump, let's say, only 10% of its total lifetime cost is actually buying and installing the pump. The rest of that cost is operations and maintenance. And so it's over 80% of the cost, the total lifetime cost of a pump happens after it's installed. And so all of those replacements or failures that we have to go fix, that all adds up to a much larger lifetime cost. And so if we can upgrade a pump, let's say we spend twice as much on a pump, but it's a much more reliable pump, that's going to make, maybe the total lifetime cost quite a bit less, because all of those failures, all of that operational, all that maintenance cost gets lowered by so much that it actually becomes cheaper in the total lifetime cost for a pump to buy way better pumps because they don't break. And so that makes sure that we can get true reliability. And that doesn't even take into account let's say a pump explodes, how many people are injured in that explosion, or how many people sadly die in that explosion. What's the effect on my relationship with my clients or the community around me that's not going to let me operate unless I go through all these really, really painful, corrective actions that, if we do a good root cause analysis, they actually fix the problem. And if we're just headhunting then and blaming people, then as people usually do in a major catastrophe, at least at the first, we're not really fixing the problem if we're doing that.
So Equifactor can help us troubleshoot, get more information about equipment problems, get our equipment operational faster, and help us learn troubleshooting strategies to improve both that learning and that speed. Where can people actually learn about Equifactor? How do they learn about this?
Yep. So we have courses all over the world at this point for Equifactor in particular. Day 1 is all the Equifactor tools. Day 2 is doing the root cause analysis for all of those equipment failures. And so everybody will learn the tools, go through the course, bring an equipment failure, like incident or accident they're familiar with, that they have data for, and then take that through the TapRooT system and really understand what a true holistic equipment troubleshooting process looks like. Because equipment troubleshooting is just the first portion, and then there's all the human performance troubleshooting that needs to go on afterwards in the root cause analysis. Yep.
So there is an Equifactor course they can take.
Yep.
They can also learn about Equifactor in our 5-day advanced. And if you're having an on-site, you can hold an extra 1-day add-on of Equifactor to a 2-day course.
Correct.
So they can learn about it in either of those things, on-site or attend one of our public courses. You can see the link somewhere down below, right here, I don't know. Somewhere there's that link to our public course page they can see. Thank you, Justin, for your time.
My pleasure.
If you want to come learn more about Equifactor, again, go check out our public course schedule. Either look for a 5-day course or one of our 2-day public Equifactor courses. Other than that, we hope to see you guys at an upcoming TapRooT course or summit. Have a great week.